Deep beneath the earth, giant machines chew through solid rock like it's butter. Every year, millions of tons of earth are shifted to create underground highways, metro systems, and utility tunnels that keep our modern world running. This is the supergiant tunneling process, where science, engineering, and sheer power come together in one of the most mind-blowing construction feats on Earth. Before we dive in, don't forget to subscribe and turn on the notification bell so you won't miss our next journey into mega engineering wonders. Tunnels are the hidden arteries of civilization. From New York's subway lines to Switzerland's Gotthard Base Tunnel, the world's longest railway tunnel, stretching 57 kilometers, these underground passages reduce traffic congestion, connect cities, and even carry water and energy. Building above ground is often easier, but in crowded urban areas or mountainous terrain, tunneling is the only solution. And that's where the real engineering marvel begins. Before a single rock is broken, engineers spend years studying the terrain, using seismic surveys, steel giant, stretching as long as 2 football fields, weighing more than 6,000 tons, and powerful enough to grind through solid granite day and night. These colossal machines are often called moles because of the way they burrow deep into the earth, creating tunnels that can stretch for dozens of kilometers. At the very front is the cutter head, a massive circular blade that can reach diameters of up to 17 meters, large enough to fit a 2-lane highway inside the finished tunnel. As it rotates, hundreds of hardened steel discs crush rock into rubble. This debris, known as muck, is immediately transported away by an internal conveyor belt system. Instead of needing trucks or carts, the TBM carries the rock out automatically, making the process smooth and continuous. But what truly makes the TBM remarkable is that it doesn't just dig, it builds the tunnel as it goes. Behind the cutter head, hydraulic arms place precast concrete segments into position, forming a perfectly round lining. Within minutes of excavation, the tunnel is reinforced, safe, and ready for decades of use. Some of the world's most famous tunnels, like the Gotthard Base Tunnel in Switzerland and the Seattle Highway Tunnel in the US, were carved by TBMs. In fact, Seattle's Bertha was one of the largest ever built, measuring 57 feet, 17.5 meters in diameter. In every sense, the TBM is not just a machine, it's an underground factory on the move, capable of excavating thousands of tons of rock every day, while simultaneously building a highway, subway, or rail corridor beneath our feet. Excavating rock on a supergiant scale is nothing short of mind-blowing. A single tunnel boring machine, or TBM, can remove up to 150,000 tons of rock every month. To put that into perspective, that's the weight of 40,000 cars being pulled out of the earth, month after month, until the tunnel is complete. The process begins at the cutter head. As the steel discs grind against solid rock, the material breaks down into fragments ranging from pebbles to fine dust. This crushed material, called muck, is funneled into conveyor belts that snake through the machine. The conveyor belts move the muck backwards at a rate of hundreds of tons per hour, ensuring the front of the TBM never slows down. Once the muck leaves the TBM, it's loaded into rail cars or massive trucks waiting deep underground. From there, it's hauled to the surface and transported to disposal sites or repurposed for other construction projects, like roadbeds or embankments. Nothing goes to waste if it can be reused. One of the biggest challenges in excavation is ground conditions. Sometimes the rock is stable granite, other times it's loose sand, clay, or even waterlogged soil. Engineers constantly monitor the geology and adjust the TBM's pressure and speed to prevent collapses or flooding. In softer ground, chemical stabilizers or even frozen soil techniques are used to keep everything safe and stable. It's incredible to think that by the end of a mega project, a TBM can move millions of tons of rock, enough material to build entire mountains elsewhere. Every ton that comes out brings the project one step closer to a finished highway, subway, or underground power line, changing the way cities function for generations. Tunneling underground is dangerous. Workers face risks like cave-ins, flooding, and toxic gases. That's why modern tunnels rely on advanced ventilation systems, pumping fresh air in and toxic air out, while powerful pumps stand ready to handle groundwater inflow. As the tunnel advances, engineers continuously reinforce the walls with steel ribs, shotcrete, and concrete linings. This ensures stability for decades, sometimes even centuries. In mountainous regions where TBMs aren't practical, tunneling still happens the old-fashioned way: drill and blast. Engineers drill precise holes into rock faces, pack them with controlled explosives, and blast away sections. Though slower, this method allows for more flexible shapes and is still used in projects worldwide. Each blast removes thousands of tons of rock, and like with TBMs, workers quickly move in to reinforce the freshly excavated area. Some of the greatest engineering feats of our time are tunnels. The Channel Tunnel under the English Channel, 50 kilometers long, linking the UK and France. The Gotthard Base Tunnel in Switzerland, the world's longest and deepest rail tunnel. The New York subway expansion, adding miles of underground track in one of the busiest cities on Earth. Each project requires moving millions of tons of rock, and each tells a story of persistence, danger, and triumph. With cities growing and traffic worsening, tunneling is becoming more important than ever. New methods like Elon Musk's Boring Company aim to make tunnels cheaper and faster using smaller automated TBMs. Meanwhile, mega projects like underwater tunnels between countries are already in planning. In the future, we may see high-speed trains shooting through transcontinental tunnels, reshaping travel and trade. It takes courage, innovation, and machines as big as skyscrapers turn sideways. And yet, it's because of these supergiant tunneling processes that we can drive through mountains, cross under oceans, and live in cities powered by hidden underground networks. If you found this deep dive fascinating, make sure to like, subscribe, and share this video. Join us again as we uncover more mind-blowing processes that shape the modern world. Small, fast, and deadly accurate, a bullet is one of the most precisely engineered pieces of hardware on Earth. Behind every round lies a combination of chemistry, metallurgy, and engineering, all executed under tightly controlled conditions where even a microscopic flaw could mean failure. In this video, we go inside one of the most secure and advanced ammunition manufacturing facilities on the planet to uncover the step-by-step process of creating a modern bullet. From raw materials to final packaging, from sheets of brass and powdered chemicals to high-speed robotics and rigorous ballistic testing, you're about to discover how firepower is forged with surgical precision. This is not just about metal and machinery, it's about safety, control, and trust. because when a bullet is fired, there's no second chance. Coming up, what materials go into a bullet and why each component is critical to performance. Before any bullet is assembled, it begins as a collection of raw materials, each selected with scientific precision for its role in creating power, control, and reliability. At the heart of every cartridge is the casing, typically made from brass. This golden-hued alloy of copper and zinc is prized not just for its durability and corrosion resistance, but for its ability to expand and contract predictably under pressure. When a bullet is fired, the brass casing expands tightly against the chamber walls, forming a perfect seal to prevent gas leakage, then cools and contracts, allowing it to be ejected cleanly. Massive rolls of brass sheet arrive at the factory, inspected for microscopic flaws before being fed into forming machines. But the casing is only the beginning. At its base lies the primer, a small metal cup containing an explosive compound that is sensitive to impact. When struck by a firing pin, this tiny component ignites instantly, creating the initial spark needed to activate the propellant. Because of its volatility, primer manufacturing takes place in specialized environments, often under robotic control, to ensure maximum safety. Workers in this section wear anti-static suits, and the process is monitored with precision cameras to detect even the slightest error. Once the primer does its job, the fire moves to the propellant, a refined chemical mixture packed tightly into the casing. Today's bullets no longer use traditional black powder. Instead, they rely on modern smokeless powder, typically made from nitrocellulose and various stabilizers. This powder burns cleanly, reducing smoke and residue, and can be tailored for specific ballistic profiles. Every grain of powder is measured with incredible accuracy, because even a slight deviation could alter performance or, in extreme cases, cause catastrophic failure. Finally, there's the projectile, the bullet itself. Usually, it starts as a lead core for weight and density, then gets wrapped in a copper or brass jacket to increase durability, reduce fouling, and enhance aerodynamic stability. These jackets are drawn from copper sheets, shaped with high pressure, and bonded tightly to the lead inside. Depending on the intended use, bullets might be shaped for expansion, penetration, or accuracy, ranging from full metal jackets to hollow points and even armor-piercing variants. Regardless of the design, they all share a common goal: delivering force with precision. Each of these components, brass, primer, powder, and projectile, is engineered independently, but they must work in perfect harmony. Together, they form the anatomy of a modern bullet: a miniature explosion chamber, a propulsion system, and a precision-guided point of impact. The journey of a bullet begins with a simple disc of brass, cold, flat, and unassuming. But in the factory, this raw material is transformed into a critical component through a process that requires extreme force, heat, and precision. The first step is known as cupping, where brass sheets are punched into small circular blanks. These blanks are then pressed into shallow cups through a powerful drawing machine. From here, the cups undergo multiple stages of drawing and annealing, a process that gradually stretches the brass into long, narrow cylinders while carefully applying heat to prevent cracking. Annealing softens the metal just enough to keep it ductile, flexible but strong. Each casing is trimmed to exact length and passed through a washing station that removes residue and oils. They emerge clean, golden, and perfectly smooth. But they're far from finished. At this stage, each casing is run through a series of progressive dies that shape the neck and mouth, form the base, and create the primer pocket with tight tolerances measured in microns. To ensure reliability, every casing is subjected to automated visual inspection. High-speed cameras check for dents, deformities, and thickness irregularities, rejecting any imperfection without hesitation. Only flawless cases move forward. Despite the rapid pace of production, the standards remain unforgiving. A single crack or off-center primer pocket can lead to failure in the field, something no soldier, officer, or sport shooter can afford. By the end of the process, that thin piece of brass has become a highly engineered pressure vessel, strong enough to contain an explosion, yet light enough for rapid cycling in modern firearms. While the casing forms the body of the cartridge, the projectile, commonly called the bullet, is the part that truly defines its purpose. It's the piece that flies downrange, pierces targets, and delivers impact. Crafting it requires a delicate balance of weight, shape, and durability, all shaped through fire, pressure, and science. The core of most bullets begins with lead, prized for its density and malleability. Solid lead ingots are fed into industrial furnaces, where they're melted down into liquid form. This molten metal is then poured into molds or extruded into long wires, which are later cut into small cylindrical pieces, each precisely measured by weight. These lead slugs will become the heart of the bullet, but a soft lead core on its own wouldn't survive the velocity or friction of modern firearms. That's where the jacket comes in, a thin layer of harder metal, usually copper or a copper alloy, designed to encase the lead and protect it during its journey through the barrel. Sheets of copper are cut into discs and drawn through a series of dies, forming cup-like shells that will wrap around the lead cores. Once the jacket and core are prepared, the two are pressed together in a process called swaging. Under massive hydraulic pressure, the lead fills the jacket cavity, and the entire assembly is reshaped into its final aerodynamic form. At this stage, the bullet's nose profile, weight, and dimensions are carefully controlled to match its specific purpose, whether it's for target practice, hunting, law enforcement, or military use. Different designs call for different levels of complexity. A full metal jacket, FMJ, offers smooth feeding and deep penetration, while hollow points are engineered to expand upon impact, increasing stopping power. Armor-piercing bullets may incorporate hardened steel or tungsten cores, offering enhanced penetration for specialized missions. Every bullet must be nearly perfect. Even the slightest deviation in weight or symmetry can affect accuracy. That's why each batch is spot-checked using digital scales, micrometers, and profile gauges. Precision is paramount. By the time the process is complete, what began as soft lead and flat copper has been transformed into a high-speed projectile capable of withstanding extreme pressure, rapid acceleration, and precise trajectory, all in a fraction of a second. Now that the brass casing has been precision-formed and the projectile expertly shaped, it's time for the most critical stage of all: assembly. This is where the bullet becomes a complete cartridge, a self-contained unit of power, accuracy, and engineering excellence. The process begins with the primer. These tiny but essential components arrive from a separate, secure part of the facility where they've been manufactured under tightly controlled conditions. In the assembly line, robotic arms carefully insert each primer into the casing's base. The fit must be snug, tight enough to hold during recoil, yet precise enough to detonate reliably when struck by a firing pin. Next comes the propellant, a precisely measured dose of smokeless powder. Automated powder dispensers ensure that each casing receives the exact amount required, down to the grain. Too little, and the bullet might not leave the barrel. Too much, and it could cause dangerous overpressure. The powder is funneled into the casing and leveled using vibration and air jets to ensure consistency. Then the projectile, the bullet itself, is seated into the open mouth of the casing. This step demands millimeter-perfect accuracy. The bullet must be pressed to the correct depth and aligned with the casing's axis. A process known as crimping follows, where the casing mouth is slightly rolled or pressed inward to lock the bullet in place. This not only secures the bullet during handling and transport, but also helps control pressure when the cartridge is fired. Throughout this stage, sensors and cameras monitor every step. Machines verify seating depth, crimp tension, and powder levels using real-time imaging and weight checks. If any cartridge falls outside of the strict tolerances, it's automatically rejected and flagged for inspection. The speed is staggering. Modern facilities can assemble thousands of rounds per hour. But despite the volume, quality is never compromised. Each machine is calibrated daily. Operators inspect samples from every batch, measuring bullet runout, neck tension, and even chamber pressure using advanced diagnostic tools. Different calibers, such as 9mm, 5.56 NATO, or 308 Winchester, require unique adjustments to tooling and timing. The machinery adapts quickly, thanks to computerized control systems that store profiles for each ammunition type. By the end of the assembly line, what started as separate components, brass, primer, powder, and bullet, has become a powerful, precision-engineered cartridge, ready for use in everything from sport shooting to military operations. Each round is identical in weight, shape, and performance. It's not just ammunition, it's consistency made real, one round at a time. Before any bullet reaches the market, it must pass a series of rigorous quality checks. In an industry where precision can mean the difference between success and failure, every round is scrutinized for perfection. Automated systems, equipped with high-speed cameras and laser sensors, scan each cartridge for defects, checking bullet alignment, primer depth, casing length, and overall dimensions.